Hello everyone, how you doing? Welcome to week 12 from my Algebra 2B class. This is the final week. We're going to be going over trigonometric properties, continuing on with what we did last week, really digging into some of the algebra with trig functions. So finish up again for this one, week 12. You got a paper pencil assignment, final quiz, do all that stuff. Make sure you're finishing this class and you're happy with your grade and have all your assignments turned in. Here's what we're going to be learning on for week 12. If I give you an algebraic equation with trig functions, sometimes you can use quadratic methods to solve it. So you could use factoring or the quadratic formula. There's ways you can use these tools to solve trig functions. We're going to go over an example of that. Finally, we're going to use, if I give you an angle measure, we're going to find exact trig values using the sum and difference properties. We're going to find the exact trig values using double and half angle properties. And then we're going to simplify and rewrite trig expressions using these properties of all this trig stuff. So sum and difference, half, double, all these kind of new properties we're going to be learning about today. So this is it. Congratulations. If you've made it to this point, you are at the end of Algebra 2 for Summit Learning Charter. Here's what we've covered this whole year. Again, we've done linear, did a couple weeks with linear systems, linear equations. We did some stuff with quadratic equations, the quadratic formula. Then we really dug into polynomials and roots. Then we got into exponential and logarithmic functions. We did some rational functions, polynomial in the numerator and denominator. We did radical functions with square roots, cube roots, and all sorts of roots. And we ended up with a lot of trig functions. So lots of functions. We use, again, different functions for different scenarios, different purposes. Anytime we're trying to use math to model what's going on, and there's different reasons to use all of them. And to kind of recap also what we did for each one of those functions, what we did was a lot of algebra. We learned how to simplify and rewrite expressions in different forms. We talked a lot about how to graph the functions, the domain and range, how I can change the equation and how it affects the graph. We did a lot with our Desmos calculator this whole year. Changing parameters, what shifts it up or down, what stretches it, what shrinks it, what reflects it, putting negatives in, all that stuff. How does that affect the graph? We would get into adding, subtracting, multiplying, dividing, whether that was polynomials, whether that was rational functions, whether it was radical functions, whether that was trig functions. We could do all of that with any of our functions. Then we get into saying, how do you solve them? You use square to get rid of square rooting. You factor, use the quadratic formula. You divide out the common denominator. All sorts of different ways for all these types of functions to get our unknown all by itself. And then we would apply it to a variety of problems. How do we use trig functions? How do we use quadratic functions? That's what we would ask ourselves. So this was kind of the pattern. We do this over and over, all this sort of process over and over for each one of our functions. And it's just good to step back and say, well, what did we just do? We just did a lot of nitty-gritty algebra, but what was the point of that? Getting comfortable with using numbers and functions in different ways and how they apply. All right, so to end on week 12, we're just finishing up with a little bit more on trig and how we can rewrite and rearrange and use different trig properties when working with trig equations. And we ended up last week talking about how do you solve them. And we could see you can take the inverse trig to get x by itself. We did some equations, but we're going to pick up on that. So here we go. We've got a quadratic equation right here. This, you should recognize this is standard form. It's quadratic, it's got x squared. And the first thing we're going to look into is it may not seem like they go together, but we can use quadratic formula or quadratic techniques to solve things that are trig. So let's take a look at this example. In this equation here, I've got 3 times the sine x squared, or sine squared of x, right? That's something squared, minus 2 times the sine of x, minus 18. And it may not jump out at you at first, but notice I've got something squared, I've got something to the first power, and then I've got a constant term set up equal to 0. If I replace, let's say I'm going to place u and say u is equal to sine of x. What I have now then is 3 times u squared minus 2 times u minus 18 equals 0. And what I've got now is a quadratic equation that I can use the quadratic formula for. Eventually, at the very end, I'll put sine of x back in, and I'll still solve the equation, but it helps me get somewhere. So let's talk about how to do this one using the quadratic formula. We're going to solve this equation. So this one I can't get sine by itself, but like what we just did, let's substitute. Let's say our variable u is equal to sine of x, and so we're going to substitute all that in here. So 3 times u squared minus 2 times u minus 18 equals 0. And the quadratic formula, a is 3, b is negative 2, and c is negative 18. All right. Let's crunch this thing out now. So u is equal to negative b, so that's going to be positive 2, plus or minus the square root of b squared, so that's negative 2 squared is 4, minus a, b squared minus 4 times a, which is 3, times c, which is negative 18, all divided by 2 times a, 2 times 3. All right, there we go. We've substituted everything in for a, b, and c into my quadratic formula. If I do some simplifying, 4 times 3 times 18, let's grab my calculator, 4 times 3 times 18, and I'm going to have 4 plus that, so plus 4. I end up with 2 plus or minus the square root of 220, all divided by 6. All right. Continuing to simplify things out here, I can change the square root of 220. 4 is a factor, so it turns into 4 times 55, but I can square root the 4 to get 2 times the square root of 55. So this radical simplifies into that over 6. And then finally, the 2, the 6, and the 2, I can simplify those down to 1 plus or minus the square root of 55 over 3. Okay, now that's equal to u, but my goal was not to solve for u. My goal was to solve for what sine of what x is, right? So here's where I need to now substitute and say, well, I'm actually putting sine of x is u. So now I've got the sine of some number, some angle, is equal to 1 plus or minus the square root of 55 over 3. Okay, now at this point, this is two numbers, right? So I'm going to solve for 2 different sines. So I need to find when does the sine of x equal 1 plus the square root of 55 over 3. And I need to solve for when the sine of x equals 1 minus the square root of 55 over 3. Well, to solve both of these, again, I'm going to use sine inverse, but let's simplify what all this stuff is first. So I'm going to pull out my Desmos calculator and do one, simplify what I got in my radicals, change it into approximately what it is as a decimal. All right, here I am. So we've got 1 plus square root of 55 over 3. And we got 1 minus the square root of 55 over 3. Now I'm noticing something interesting here, right? My sine of some number was supposed to be equal to one of these numbers, right? But 2.8 and negative 2.13, I know I have a problem because both of those numbers, there's no sine of any angle that equals that. To have sine of a number, it's going to be between negative 1 and 1. And these are outside of the range of possibilities. So at this point, I can conclude Since one number is about 2.8 and the other is negative 2.1, let's go back here. So we lost all our previous algebra, but that's okay. But now we've got the sine of some number equaled 2.8. That was one of the solutions. And the sine of a number equaled, let's see what the other one was, negative 2.1. And for both of these, there is no angle that'll give me that sine value. So at this point, I'm done. Now, if I was curious, if I really wanted to check, let's graph this and see if there are any points where it equals 0. So I'm just going to graph this whole entire equation just because I want to double check. It seems like there's no solution, but I want to double check just to make sure. I'm going to put all this in, graph this, and see if there's ever any angles that give me equal to 0. All right, here I'm back in my Desmos calculator. I'm going to put in, we had 3 times the sine of x squared minus 2 times the sine of x minus 18 equals y. And I'm going to zoom out, and there's the problem, right? We graphed this. Are there any points where we have a value of 0? I never get a y value of 0. It's shifted down so far that it makes sense why there's no solutions. It's undefined because there's no angle that'll give me the values that I need. So graphically, there are no points where it equals 0, and this is confirming the algebra we just did as well. I'm feeling much better about my answer. Whew. All right, let's go back. So recapping what we did, we solved this basically with the quadratic formula, but instead of, and then put sine of x in at the very end, but found that there is no solution, right? Sine of x has to be between negative 1 and 1, and our values were asking for 2.3 and negative 2.1. But we weren't sure, so we graphed it, and we saw that if I graph this as well, there is no point on this graph where I get a y value of 0. It's shifted way down because of this negative 18. So that made me confirm that, yep, there is no solution. But anyway, there we go, solving trig functions, using algebra to solve it, but then graphically checking our work and understanding what's going on as well. Okay, let's solve this one. What do we got going on here? This one I got a sine and a cosine. How do I deal with solving this? Well, one other strategy is to use the Pythagorean theorem formula. Remember, we know that sine of some angle squared, sine squared of an angle, plus the cosine squared of an angle, they have to add together to equal 1. That's straight from the Pythagorean theorem. It was one of the identities we did last week. So if you want to solve something like this, the only way I can solve it is to have both, to have just sine or just cosine. In this case, I have both. So let's do some substitution. I'm going to rearrange all this to subtract sine from both sides. So the cosine squared of a number equals 1 minus sine squared. And then I'm going to square root both sides. So the cosine of a number equals the square root of 1 minus sine squared of x. And that's what we're going to do. We're going to substitute this in for this cosine, and then we'll only have sines left. All right, so what's my new problem now? So now we've got 1 minus the sine of x is equal to the square root of 3 times the square root of 1 minus the sine squared of x. Now you may feel like that did not help us very much, but it actually does. It actually does. We'll show you from there. So now I want to do some things to rearrange it. I've got a bunch of square roots on the right side. Let's just go ahead and square everything on both sides to undo the squaring. And what do we get? On the left side, I got a binomial, so we got 1 squared minus 2 times the sine of x plus sine squared of x, that's what we do when we FOIL this thing out, equals, I'm squaring all this, so the square root of 3 squared turns into 3 times, all this was square rooted, but it undoes with the squaring, so now it's just 1 minus sine squared of x. It's looking a little bit cleaner now. Let's distribute the 3 and start to simplify things out. So we got 1 minus 2 times the sine of x plus sine squared of x equals 3 minus 3 sine squared of x. Now let's get everything onto one side. So let's see, I'm going to add 3 sine of x squared to both sides. So that's going to give me 4 times the sine squared of x minus 2 times the sine of x. And we'll subtract 3 from both sides to be minus 2 equals 0. I can factor out, so there's a common factor of 2. So let's make this 2 times the sine squared of x minus sine of x minus 1 equals 0. Essentially, I divided both sides by 2. So we're simplifying this down, and now I've got actually another quadratic form again, right? I've got a trig function squared, a trig function of the first power, a constant, and it's equal to 0. All right, what's nice in this one is I could jump to the quadratic formula, but remember, we can also solve quadratic equations by factoring. Let me rewrite this out as 2 times x squared minus x minus 1 equals 0. And now that I look about it just in this way, again, I just replaced x with sine of x, I can see that it actually factors down pretty nicely. Factors into 2x plus 1 times x minus 1. And again, you can check it. 2x times x gives you 2x squared. 2x times the negative 1 gives you negative 2x, but now we got a plus x. And 1 times negative 1 gives you negative 1. So it factors into that. But let's go back to original problem. I didn't want x, I wanted sine of x. So really we've got 2 times the sine of x plus 1 times the sine of x minus 1. And when do those equal 0? All right. Again, we're using factoring, we're using quadratic methods. So when does 2 times the sine of x plus 1 equals 0? We have solved for this first one right here. Well, if I subtract 1 and divide by 2, that's the same as when does the sine of what angle equals negative 1/2? Ooh, that negative 1/2 should really stand out as something that we can use off the unit circle, right? Let's look at the other one. When does the sine of an angle minus 1 equals 0? Well, if I add 1 to both sides, that's the same as the sine of what angle equals 1? Well, that's another one. We know that one is too. So let's look on my unit circle and see what angles give me negative 1/2 for sine and positive 1 for sine. I already know the positive 1. That's when it's straight up. So that's going to be when x equals 90 degrees. But now let's find out when is my sine value negative 1/2. All right, here I'm on my unit circle. I'm looking for the sine of what angle gives me negative 1/2. Sine is your y value. There's when the sine of the angle equals 1, so that's 90 degrees. That's one solution. Negative 1/2 will be at 210 degrees right here. There's a sine value that's negative 1/2. And at 330 degrees. So there's two different angles that give you a value, sine value of negative 1/2. 210, 330, and 90. So we got 3 solutions. So in solving this out, what angles do we find? We found that when x equals 90 degrees, 210 degrees, and 330 degrees. Now really we should pop these in and actually check our solutions. Put them in for x, calculate them out, and see if they actually do indeed work out. But there you go. We just solved some stuff. Okay, so switching on, that's enough with solving equations. I think you got some good tools now and hopefully some good examples to solve trig functions. Now we're going to get more into the nitty-gritty and finding trig values, being exact with our trig values, and just some other properties. So we've already learned the Pythagorean theorem, how it helps us. We even did an example about using that to substitute. There's also the sum and difference properties. So here's all the sum and difference properties and the ways we can use them to rewrite it. And I'll show you how it's helpful. So we know from our unit circle and from our special right triangles, we can find 30 degrees, 45, 60, or 90 degrees, or any multiples of them. But what if I said, what is 50 degrees? Or what is 75 degrees? Those aren't straight up as obvious, but we can use some of these properties to help us find other exact trig values. And again, when I say exact, I mean exact, not to where we have to round something. Because we can use our calculator to calculate sine values and cosine values and approximate them and round them to whatever decimal we want to round them to. But if we want to find exact, then we need some of these values. And all this is saying is we can split things into some angles and rewrite them differently. So let's do an example about how to use the sum or difference. Find the exact value of the following, the cosine of 195 degrees. All right, well, the cosine of 195 is not anything that shows up on my unit circle, but here's where the sum or difference. I can think about this as 195 equals 135 plus 60, right? So I could rewrite the problem like this, and this would be the sum. So 195 is the sum of 135 plus 60. The nice thing is 135 and 60 are two angles that I can find straight off on the unit circle. So let's go look up the formula for the sum of cosine. And then let's look up 135 and let's look up 60. And then we'll come back and we'll tackle this problem here. All right, first thing, if you go to Algebra 2 Live, you say, where are all these formulas? I have a nice formula sheet listed out for you under week 11, right here, Trig Math handout. And if you open it up, you have all of these properties right here, right? So Pythagorean theorem identities, reciprocal identities, basic ratios. There's some other Pythagorean theorem ones, negative values. We're going to come over here to sum and difference. And remember, we were looking at the cosine and splitting it up in the sum of two angles. So this is the formula that I need for the problem that we're working on. So the cosine of the sum of two angles is equal to the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. So I got that down. This is the formula I need, the trig identity. Now I need to know the cosine and the sines of these different angles. Remember, it was 135 and 60. So let's go to the unit circle and let's look these up. So 60 degrees, the cosine of 60 is 1/2. The sine of 60 degrees is the square root of 3/2. Now the other one I needed was 135, so that is right over here. The cosine of 135 is negative square root of 2/2, And the sine of 135 degrees is positive square root of 2 over 2. So now I've got everything I need. Let's go back and calculate what the cosine of 195 degrees is. Okay, so let's break down some of these formulas. We know the cosine of the sum of two angles, u and v, is equal to the cosine of u times the cosine of v minus the sine of u times the sine of v. Now, if you're really at all curious, you could look it up and say, well, where does this come from? Who made up this thing? That gets into more calculus, proving things. It's more into high-level math. For now, you just have to assume that, yep, mathematicians have shown that this is true. But we got, all right, so this is our formula. And then we rewrote that into the cosine of 135 degrees plus 60 degrees. Those add up to, and so we're using the sum. So in this formula, I'm going to replace u with 135 degrees and v with 60 degrees. And now let's rewrite this whole thing out. So we've got the cosine of u, which is 135, times the cosine of 60 minus the sine of 135 times the sine of 60. Whew, okay. Fortunately, I know these values, right? The cosine of 135 degrees. We wrote that down straight off the unit circle, was negative square root of 2 over 2. And the cosine of 60 degrees was 1/2. Minus the sine of 135 degrees was positive square root of 2 over 2. And the sine of 60 degrees was square root of 3 over 2. Good thing we're good with our square roots, right? But again, what did I just do? We split 195 into the sum of two angles that we know the exact values. We used our formula to rewrite it out. And then we substituted the exact values straight from our unit circle. And now we're going to simplify this out. Just do some math with radicals. So if I simplify this first, negative square root of 2, this is going to turn into negative square root of 2 over 4. That's 2 times 2 on the bottom there. And over here we get the square root of 6 over 4. And so if I subtract those, negative square root of 2 minus square root of 6, they're not like radicals, so I have to leave them as separately. Negative square root of 2 minus the square root of 6 over 4. And that is going to be equal to the cosine of 195 degrees. That is the exact value right here. Now, what if you don't feel very confident in your work, right? You feel a little bit shaky on this. How do we go check it? Again, as mathematicians, we want to be able to check reliably, know if we did things right or not. Well, we can do a quick check just by using our calculators, right? We can put in this, calculate what the decimal is, put in the cosine of 195 and calculate what the decimal is and see if they're equivalent. So let's do that. Let's go ahead and check and make sure we did all of our math correctly here. Here I am in my decimal calculator. So first let's put in negative square root of 2 minus the square root of 6 divided by 4. And we get this value right here, negative 0.9659. All right. That should be the exact value of what the cosine of 195 was. But now let's put in the cosine of 195. Let's make sure we're in degree mode. And what do we got? Look at that. I'm feeling really good. These are the exact same numbers. So this is exact. This is the decimal equivalent, and this is also the decimal equivalent. Since these are equal, I'm feeling really good that these are equal. Now, square root of 2 minus square root of 6 over 4 is an exact answer. This, as close as it is, and as to the millionth decimal, whatever, it's still not exact. This is a decimal approximation because it goes on infinitely, whereas this is exact. But this is how you would check your work as you're finding exact trig values. You can come in and calculate them and make sure they're reasonable. If they're significantly different, then you probably made a mistake somewhere. But now I'm feeling really good that the cosine of 195 degrees is exactly this value right here with all the radicals. All right, what about this one? Here I've got the tangent of negative 75. How do I go about working this out now? All right. So I've got difference angles. I need to think about, can I rewrite negative 75 degrees as the sum or difference of something? Well, I can know negative 30 degrees, and I can know negative 45 degrees, right? And so it's the sum of those two negative angles. The other thing I could do is say, well, that's the same as the negative tangent of positive 75. So I could instead, if I don't want to deal with the negatives here, I could say, well, let's calculate the tangent of 75 and think of that as 30 plus 45. And then at the very end, make the whole thing negative. But I'll just do this. I'll work with both negative values because it'll work. It'll get me to what I need. So I need to find the tangent of these values. I need to find the cosine, the formula, and all that kind of good stuff as well. All right, so I got to go to all my different formula sheets. So here I am at the math handout. I need to find the tangent of the sum of two angles. So here's the formula for tangent. I'm going to jot that down real quick here. So the tangent of two angles added is equal to the tangent of the first angle plus the tangent of the second angle divided by 1 minus the tangent of the first angle times the tangent of the second angle. Okay? Now I need to find the exact tangents. Remember our angles, we split 75, negative 75 into negative 30 and negative 45. So let's do that. Let's go to my unit circle. So negative 30 degrees is going to be right here. So the tangent at negative 30 is equal to sine divided by cosine. So it's negative 1/2 divided by square root of 3 over 2. And if I simplify those out, that's just going to become negative 1/2 times 2 over square root of 3. It's just negative 1 over square root of 3. Okay? Now I need the tangent of negative 45. So if I go on negative 45 degrees, that's right here. The tangent of negative 45 is sine divided by cosine. So that's negative square root of 2 over 2 divided by positive square root of 2 over 2. They're the same number, just one positive, one negative, so they actually turn into just negative 1. So that's going to be really, really nice. So now we got our values, we got a formula. Let's go back and do this problem. Okay, so my formula, if you remember, the tangent of the sum of two angles, u and v. The formula says take the tangent of the first angle plus the tangent of the second angle divided by 1 minus the tangent of the first angle times the tangent of the second angle. Now we split this into the tangent of negative 30 plus negative 45. I know we looked up on our unit circle the tangent of negative 30 degrees is negative 1 over square root of 3. And the tangent of negative 45 degrees was negative 1. All right, let's put it all together. So there's my 30. So in here I'm going to do negative 30. That's going to be negative 1 over square root of 3. That's the tangent of negative 30 degrees right here. Plus the tangent of negative 45. That's negative 45 degrees, which is negative 1. So negative 1 over square root of 3 plus negative 1, that's in my numerator, divided by 1 minus, and then multiply them. So negative 1 over square root of 3 times negative 1, just like that. Looks great, right? Let's simplify this thing down. In the numerator, I'm going to change negative 1 into negative square root of 3 over square root of 3, so I get common denominators. So negative 1 divided by square root of 3 plus negative square root of 3 over square root of 3. In the numerator then, that's going to be negative 1 minus the square root of 3 all over the square root of 3. And in the denominator, these multiply to make a positive 1 over square root of 3. I'm going to change this into square root of 3 over the square root of 3. So I have common denominators here. And now I can get the square root of 3 minus 1 all over the square root of 3. Okay, so we combined terms, did a little bit of rational work here. I can rewrite this instead of a division problem into a multiplication problem by the reciprocal. So we got negative 1 minus the square root of 3 over the square root of 3 times the square root of 3 over the square root of 3 minus 1. Kind of making our way through the algebra, right? Switch colors to make it a little bit cleaner. Here's what's nice. The square root of 3's divide out. And so now we've got negative 1 minus the square root of 3 divided by square root of 3 minus 1. Now what I want to try and do here is these are like almost identical, right? I really want to see if I could get them to become the same thing, although I don't think I can because this one I've got positive negatives. This one both the terms are negative, whereas this one only the 1 is negative and the square root of 3 is not. I think if I really wanted to, I could multiply the bottom. Yeah, let's go and do it. Let's go and do that here. I'm going to make some room out there. Let's rationalize the denominator and see what happens. So negative 1 minus the square root of 3 over the square root of 3 minus 1. And I'm going to multiply by the square root of 3 plus 1, the conjugate. And let's see if we can get some things to simplify down. Got to FOIL these out. Square root of 3 times the square root of 3 equals 3. Square root of 3 times 1 is plus the square root of 3, but then I have negative 1 times the square root of 3. So the middle term is going to cancel. And then if we got negative 1 times 1 is going to be minus 1. So in the denominator, it just turns into 2, which is kind of nice. But now let's see if anything shakes out or simplifies nicely in the top. So negative 1 times square root of 3 is going to be negative square root of 3. Negative 1 times 1 is going to be minus 1. Negative square root of 3 times the square root of 3 is going to be minus 3. And then the negative square root of 3 times 1 is going to be minus the square root of 3. It doesn't simplify as nicely, right? We get negative square root of 3, we have negative 2 square root of 3, because there's 2 of them, minus 4 over 2. But I can divide some things out, so really my final answer then would be the tangent of negative 75 degrees is equal to, the 2's divide, it's negative square root of 3 minus 2. That's actually pretty good. That's not too bad, right? How would I check it? I would go into my calculator, I'd calculate the tangent of -75, and I'd calculate this, and they should be the same value. But there again, we had to do a lot of algebra work, I had to get the right formula, to look up the exact tangent values, substitute them in, and then it took some work to simplify things down. We had to be really comfortable with all our radicals. That's why we did a whole couple weeks working with radicals. How do we add, subtract, multiply, simplify? We had to do all those skills from earlier in this. Hopefully you were able to follow along to all this as well too. All right, we did a couple examples of using the sum or difference. There's also properties involving doubling or taking half of the angles. So here's all the formulas on if we have the sine of an angle, but I want to double the angle. What's the sine value of it? Cosine, cosine, cosine. There's a few different ones for cosine and then a tangent. Or what if I have an angle and I want to take half of it? There's a formula that we can use for that as well too. So we're going to do two more examples, one doubling and one halving, and showing you the algebra, how we can rewrite and find exact values, and then we'll be done. So hang in with me, here we go. The cosine of an angle is 0.25. What is the sine of twice that angle? All right, so what do we got? The cosine of some angle is 0.25. How do I find the sine of double that angle? Well, remember, we want to find an exact value. So what I need to do to be exact is remember that the cosine, let's rewrite 0.25 as 1/4. And remember that the cosine is also the adjacent side divided by the hypotenuse. So if I apply the 1 and the 4 to a triangle, the angle is the adjacent side, 1, the hypotenuse is 4, and there's my cosine. So there we're starting together, putting together the kind of the ratios of what we know. Cosine of that angle. I don't know what the angle is, but I know the adjacent side divided by the hypotenuse side has to be 4. And if I know that, I can solve for my unknown angle by using the Pythagorean theorem. 1 squared plus my unknown side b squared should equal 4 squared. 4 squared is 16, so really b squared is 16 minus 1, 15, which means b equals the square root of 15. Now I can get into finding the sine. If the cosine of an angle is 1/4, the adjacent divided by hypotenuse, the sine is going to be the opposite, the square root of 15/4. And we just found the exact value. Now I could have done cosine inverse, and I could have got a decimal angle, and then I could have found the sine of it, but it would not have been exact. This is exact, keeping all the square roots. Remember, square roots are just get really irrational, and anytime you have to turn them into decimals, you're not exact anymore. Okay, so the sine of an angle is square root of 15/4. What is the sine of twice that angle? So now I've got to write all this stuff down. I'm going to write down sine of an angle is square root of 15/4. But I want to know double the angle, so I got to go look up on my formula for what is the formula of the doubling of sine. Here I am on my sheet. There's my sum and differences. Where are my... There we go. Double angle identities. The sine of twice an angle is equal to 2 times sine of the angle times the cosine of the angle. All right, so I'm going to write that formula down. 2 times the sine of that angle times the cosine of that angle. All right, let's go back. I got my formula, and now I know how to find the double angle. Okay, so what do we got? We already know the cosine of that angle was 1/4. That's what we were given. We did our Pythagorean theorem. We worked around to find the exact sine of that angle was the square root of 15/4. So now the sine, using my double angle formula, the sine of twice an angle, 2 times that angle, we had this formula. It was 2 times the sine of the angle times the cosine of the angle. But we already know all those values, so let's substitute them in. I'll put 1/4 for cosine. I'll put square root of 15 over 4 for the sine times 2. Let's simplify this all out. 2 times 1, so that equals 2 times the square root of 15. In the numerator, think of that 2 as 2 over 1. And then on the bottom, I've got 16. We can simplify that into the square root of 15 over 8. So that is going to be what sine of twice the angle has to equal. Square root of 15 over 8. Now, how would I check that? Well, here's where I could go back to my calculator and do some stuff. So if I want to, let's actually show how to check this on the Desmos calculator. Make sure we're doing our doubles and half angles correctly. All right, remember how in the problem we had the cosine of some angle was 1/4, or 0.25, right? So let's actually find what the angle is using cosine inverse of 0.25, and we see that it's 75.52 degrees. All right, so let's find out what the sine of 75.5224878,141. That's what the sine of that angle would equal. But we wanted to double it, right? And let's just double check. So we found the sine of that angle was exactly square root of 15 over 4. Let's just check our square root of 15 over 4. Oh, look at that. So there's the sine of the angle. We exactly figured it out from the Pythagorean theorem of square root of 15 over 4. But we can check it as well too using our calculator. So right now I'm already feeling pretty good about what the square root of 15 over 4 is. Now the sine of double that angle, I would take this, let's copy that down, and let's multiply it by 2. So now there's the double the angle should equal this value. And we said, well, that's the same as the square root of 15 over 8. That's what we calculated with our double angle formula. And look, it's the same value as well. So we were able to calculate the exact value algebraically using the formula, but this is how we would check it on the Desmos calculator, making sure the decimal and the exact value that you get the same values when you check your work. So we did good. I'm feeling really good about this. I'm feeling really good about this example for you. Hopefully you followed how we calculated all these and made sure our numbers matched up. All right, final problem. The previous one we did a double angle. This is going to be an example of using the half angle formula. How do we find the exact value? Again, there's our trick. The exact value of the following, 3 pi over 8. Well, on my unit circle, I don't have anything around with eighths, but we do have stuff with fourths. I can actually look up and see the cosine of 3 pi over 4. We're able to find that exact value, right? In fact, that cosine would be negative square root of 2 over 2. But 3 pi over 4, if I multiply it by 1/2, that would be 3/8. So what we need to do is find out what's the cosine of 1/2 times 3 pi over 4. And we're going to use the half angle formula because we can figure out this part and probably use it. So we're going to use the half angle formula. I need to find it for cosine, and then we'll finish up this problem. All right, here's my trig sheet. Let's find half angle identities for cosine. And there you go, the cosine of half of an angle. I'm going to write this down. Is equal to plus or minus, okay, the square root of 1 plus cosine of the angle divided by 2. So what we need to know is double check, well, we had 3 pi over 8. What's 3 pi over 4? Let's just double check that on our unit circle. So 3 pi over 4 is right here. That's the radian measure. The cosine then is, yep, it's a negative square root of 2 over 2. So in our formula, the cosine of half of an angle is equal to plus or minus the square root of 1 plus cosine of whatever that angle is divided by 2. But what do we know? We already looked up that our angle, we said the cosine of half of 3 pi over 4. And we already know, we looked up on the unit circle, the cosine of 3 pi over 4 is exactly negative square root of 2 over 2. Let's combine all these things together and we can start calculating this out. So the cosine then of 3 pi over 8 is going to be equal to plus or minus the square root of 1 plus the cosine of the angle before it's been divided, we already know is negative square root of 2 over 2, all divided by 2. There we go. Now we just got to do the hard work of simplifying it down. So what I'm going to do here is let's combine these two top terms. Let's change 1 into 2 over 2. Because 2 over 2 is the same as 1. Now I've got a fraction with common denominators, so that equals plus or minus the square root of 2 minus the square root of 2 all divided by 2. Combine those, but then the whole thing is again divided by 2. Well, if I simplify what's inside the radical, change your division problem into multiplication with the reciprocal, that's 2 minus the square root of 2 over 2 times, instead of 2 over 1, it's times the reciprocal, 1 over 2. And now we can multiply across to get that it equals plus or minus the radical. All in the numerator, it's just still 2 minus the square root of 2. And in the denominator, 2 times 2 is 4. But there's still a little bit more I can do here. The square root of a fraction, I can take the square root of the numerator, square root of the denominator, so I can rewrite that as the square root of 2 minus the square root of 2 over the square root of 4. That's still plus or minus. But the square root of 4 it just becomes 2. So it's plus or minus the square root of 2 minus square root of 2 over 2. And there we go. We have just found the exact values. Whew. I'm not going to check this because I think we've checked a couple. I think you have an idea about how to go in your Decimalist calculator and actually confirm this, the plus or minus. So that means the cosine of this angle, here's where you'd have to double check on, are we wanting to find the positive or the negative value of that. 3/8, so the cosine should be negative because, well, no. This is a little less than half. The cosine of pi over 2 is exactly 0. So the cosine of this should be positive because it's in the first quadrant for this radian. So we would take the positive value of this. All right. Whew, well, there we go. We went through a lot for week 12. We covered all these solving equations, did a couple examples there. We did a lot of examples with different trig properties, different formulas, different ways to rewrite trig values and find exact trig values using all your triangles, using all your ratios. Hopefully you got a good idea about how to use the unit circle some more and how to use the different trig identities, finding the right formula that you need to rewrite the problem. Let me know if you have any questions for this week, and I look forward to helping you get this class all done. Good work.